take a moment to press pause and read the entire question prompt. Here we have a problem where we have a car that is traveling on a long, straight road. This is a key word that is telling us that we're going to have one-dimensional motion. The car speeds up at a steady rate, holds its speed for another time interval, and then decelerates and slows back down. We can see here that it accelerates at a steady rate. That's another key word telling us that that is constant acceleration. We're told later as well that the car is decelerating, and we're given a value. We can see that this is a number, a fixed amount, and so that is also constant acceleration. For another part of the motion, we're told that the car maintains a speed. So we don't know what that speed is yet, but we know that it's maintaining the speed. It's keeping a constant speed, which we call uniform motion. So we've read through the question prompt, and we have looked for some clues that will tell us how we should approach this problem. The first thing that we should do to actually solve it is to draw a picture representing the motion of the car. Again, click pause and draw your own picture, and then we'll come back together and compare. So we have a long straight road, which we're representing as one-dimensional motion, and so we'll use an x-axis to measure that distance. The car is at a stoplight, so that makes sense for us to call that our origin. When the light turns green, the car is going to accelerate. We have a constant acceleration there, and it reaches its cruising speed at 82 meters down the line. So we have a constant acceleration this whole interval. We don't know what it is, but we know that it's some fixed value. We know that our car begins at rest when it stopped at a stoplight, and it hits some speed that we don't know what it is, but we can find that. We're also told that this acceleration lasts for 7 seconds. So we know that the time increment here is 7.4 seconds during this first interval. We go from 0 to 82 meters, and so our displacement in that case is going to be that 82 meters there. Now the car has hit its cruising speed. The car is going to maintain that speed for another 11 seconds. And so if the car is moving with some constant speed for 11 seconds, it's going to go some further distance down the line. We know that the time here is 11 seconds. We don't know the distance. We can call this delta x2 because that's the displacement during the second portion of that motion. And we know at the end of that motion, the car is going to be traveling, and it's going to have some velocity. V1 was the velocity at the end of the first increment, but if we're going at a constant speed, it's going to have the same velocity at the beginning and the end of those segments. And then finally, we see that there's another stoplight coming up, so the driver is going to begin to decelerate. It decelerates at 6.59 meters per second squared. Decelerate is a word that's commonly used by non-STEM folks. All that means is that they are slowing down. So in this case, we assume that the car is moving to the right. And so for us to be slowing down, that means that the acceleration needs to be pointing to the left. And so our deceleration here really means that we have a negative acceleration of 6.59 meters per second squared, which is going to cause the car to slow down and stop. We're told that the car comes to a halt, which means that we're going to end up somewhere down here. We'll call this a displacement, delta x3, as the displacement during this third portion. And we know that the car is going to come to a halt, so its velocity is going to be 0 at the end there. And so what we are asked is to find the initial acceleration. The initial acceleration would be the acceleration during this first time interval. We want to find the magnitude of the car's average velocity during this whole motion, and then we'll draw position, velocity, and acceleration graphs. So to find the initial acceleration, we'll focus on this first time interval. We know that the acceleration is constant, and so we'll be able to use our constant acceleration equations to find the the acceleration we have during that interval. So for us to pursue part A, we want to find the initial acceleration during an interval of constant acceleration. So what we'll do is write out our constant acceleration variable so we can figure out what we have and what we're trying to find. We know that the car is initially stopped at a stoplight, so we know that its initial speed is going to be 0 meters per second. We don't know the acceleration. That is what we are trying to find. We do know the distance that the car travels during that period of acceleration. And we do know the amount of time that it takes for us to achieve that change in speed. So take a moment to, we see here that we have 3 variables. We have 3 pieces of information. We can use that to find the 4th value. Take a moment to hit pause and figure out which of the constant acceleration equations we should use based on this information of what we know and what we want to find. In this case, we don't know V final, so we're going to use the equation that doesn't have V final in it. And this is the equation that we'll use. We will plug in the values that we have and solve for our acceleration. And we could evaluate with our known values. This term is 0 because we have 0 initial velocity, and we can find the acceleration, which is approximately 3 meters per second. Now that we know that, we can add that 3 meters per second squared into our understanding of what is going on here in this problem. The next thing that we're asked for part B is to find what is the magnitude of the car's average velocity during this motion. So if we're looking for average velocity, hit pause for a moment and think of what average velocity means. It is the total displacement over the total time for the entire interval. So in this case, we know the displacement in the first part. We know the time. We know the time for the second segment, but we don't know the displacement. And for the third portion, we don't know either. So what we'll need to do is we'll need to find the displacement here, and we'll need to know the displacement and the time for this segment so that we can find the total displacement and the total time. What we'll need to do to find the displacement in this portion, where we have uniform motion, there's only one equation for us to use for uniform motion in segment 2. And that is that the displacement is the speed times time. So if we want to find out what our displacement is here, we'll need to know what the speed is in this segment. We don't have very much information about this segment, but we know that the car is speeding up during this interval of constant acceleration, and then it holds that speed. So what we can say is that the speed in this segment is going to be the same as the final speed during this segment, because the car is speeding up. The final speed that it has here is going to be the initial speed that it has here, and it's going to maintain that speed this whole way through. So we'll have to go back to our first segment, this information that we have over here, and we'll need to find the final velocity for this first segment here, find this final velocity, because that'll be the initial velocity here that we have for the second segment. We have this initial velocity. We know all the other values, so we could use any equation, but since there are rounding errors already in the acceleration, we want to try to avoid using acceleration to find the final velocity, so we can avoid propagating those rounding errors. So take a moment to pause and determine what equation you'll use to find the final velocity. This is the equation that we'll use here. It doesn't have acceleration in it. We'll plug in our known values and we'll solve for the final velocity. And we find this to be our final velocity for our first segment here. We see that we have 3 sig figs everywhere else, so I'm going to use at least 4 sig figs here to minimize rounding errors. I'm going to use these for my calculations, and I'll round to sig figs at the end. So we found this value here. That's our speed at the end of the first segment, which would be the speed at the beginning of the second segment, and that would be our constant speed here while we have uniform motion or motion with constant velocity. So we know the speed that we have in that interval, and we know that this interval is 11 seconds long. And so we'll be able to use our equation for uniform motion to find the displacement during this interval. And we found the displacement, how far the car has traveled during this interval here. So we can erase this part here and put in instead the value that we have. Now we still need to know the displacement and the time for this third segment here. We also have constant acceleration here. So if we know that we have constant acceleration during this interval, the first thing to do will be to write out the constant acceleration variables like we did before and figure out what we know and what we're trying to find. For this third segment, we're told that the car is brought to a halt at the end of the segment. We said that the velocity here would be 0. That's our final velocity. We're also told the acceleration in this case. We're told that we're slowing down. That's something to do with the car and the car's ability to stop. In this case, we're slowing down, so that needs to be a negative 6.59 meters per second squared. Deceleration means that you're slowing down, and so that is a non-scientific term, and we have to interpret that. If we're slowing down, in this case, that means we would have a negative acceleration. We need to find the displacement of the time, so we need one more piece of information. We're going to be looking here. We don't know anything specifically about the initial velocity here, but we know that the final velocity in this segment is going to be the initial velocity of this segment as we transition from uniform motion to constant acceleration. So if we're moving at 22 meters per second here, we're still moving at 22 meters per second at the very beginning of this interval. So we can go ahead and use that value here as well. Notice again, I'm still using 4 sig figs here to maintain my accuracy, and I'm going to round down everything at the end. So here I have 3 pieces of information. I want to find displacement and time. So the first thing I'll do is find displacement. I don't know time, so I'm going to need an equation that doesn't have time. Click pause and think of what constant acceleration equation you would use here. This is the equation that we would use. We would evaluate it using our known values, and we can find the displacement that we have as a result. We'll do the same thing to find time. I know here, first of all, that my displacement should be in meters. As long as I used proper units at the beginning, I should get proper units for displacement at the end. Notice also this is a rounded value, so I don't want to propagate my rounding errors. So if I'm trying to find delta t, I'll use a different equation that involves all of these quantities. Take a moment to click pause and think about what equation you're going to use. And so I've found also the time that it will take to bring the car to a halt over this third interval. So now we're trying to find the magnitude of the car's average velocity. We said the average velocity is going to be the total distance divided by the total time. Well, our total distance is 82 meters for the first segment. It is 243 meters for the second segment, and it is 37 meters for the third segment. So we can find our total time then. And we have our overall displacement here. We also need to look at the total time it takes. We know the first segment was 7.4 seconds. We know the second segment was 11 seconds, and the third segment was 3.36 seconds, so we can find the total time as well. And we have our total time, and then our average velocity over this total interval is the total distance divided by the total time. .73 meters per second. We have 3 sig figs, so we'll cut that down to simply 16.7 meters per second, which also makes sense. We start out at 0 and we speed up to about 22 meters per second. That's for the longest period of time. About half of our time interval is at 22 meters per second. We're slowing down, so our average value is going to be less. We're speeding up, so our average value is less. We're slowing down here, so the average value is also less. So if you average 22 and going from 0 to 22 and from 22 back to 0, 16.7 is in that region, so that makes sense for us as well. Finally, what we're asked to do is to find position, velocity, and acceleration graphs for this motion. So we need to know the velocities for each segment, segments 1, 2, and 3. I'm going to erase all of this portion here. So the easiest place to start looking at the position, velocity, and acceleration graphs, the easiest place to start is with the acceleration. So we'll start by drawing a graph for ourselves. We know that this graph should go from 0, and then it should take the total time for this whole segment. So my entire time interval is not quite 22 seconds, so I make sure that my time axis goes out to 22 seconds. And I look at my accelerations. One's at 3, 0 acceleration here when we have uniform motion, and then here I'm at -6.5. So in this first interval, my acceleration we found to be 3, and that lasted about 7 seconds, not quite 8 seconds. So my acceleration is at 3, and it's about just before 8 seconds. Then in this region here, I have 0 acceleration, and I'm going from just before 8 seconds. I'm going 11 seconds more than that. So that would be 4, 8, 10, and a little bit more. And my acceleration is going to be 0, so it's going to be right on the axis, just about there. And then in this third segment, my acceleration is -6.59. It's negative, so it's going to be below the horizontal axis, and it lasts the final 3 seconds or so. And so this would be -6. I'm going to be just a hair below that. And that would be what my acceleration would look like, more or less. My next thing is to look at my velocity, so I'm going to do basically the same thing. In this case, my velocity goes from 0 up to 22 meters per second, and from 22 meters per second back down to 0. So my time interval is the same. I'm going to use the same time interval, but I'm going to use a vertical axis that goes from 0 to 22, and then from 22 back down to 0. So in this graph here, I have my velocity goes from 0 to 22, and my time runs from 0 to about 22 seconds as well. So I know that my velocity begins at 0 at time t equals 0. And I know that at the end of my first interval, at just before 8 seconds, that's when I hit that speed of 22 meters per second. So right at the end of the second interval here, or the end of the first interval, beginning of the second interval, I'm hitting that 22 meters. So that means that I am somewhere around here. Also, I know that if I have constant acceleration, a constant value is a horizontal line. If I have a constant acceleration, that means I have a linear velocity, and so my velocity should be a straight line in this case. Then I maintain that constant velocity for 11 seconds. If this is a constant velocity and I'm graphing velocity, a constant velocity should be a horizontal line, and I'm going to maintain that for 11 seconds. To about there. And then I make it all the way back to 0 at the end at just before 22 seconds. So I know that I'm going to end up back at 0 right about there. And I know that I have a constant acceleration here as well. So I have a linear velocity here. And so I know my velocity should be a straight line. This is about twice as steep as this because the acceleration here is about twice as much as that. This is angled upwards because I have a positive acceleration. This is angled downwards because I have a negative acceleration. And then finally, I can look at my displacement. In this case, I'm going to need to give my full, find the full displacement, which in this case is going to be 300 some meters. And I have the same time interval that I'm looking at here. So here I have my full position graph. I go from, if I call this 0, I go 82 meters, and then 243 more, and then 37 more. That gets me right around 350 meters total. My time interval is the same as it is before. I cover all this distance in the same amount of time. And so what I did here was I assumed at the very beginning, I just called the initial position of the car as 0 as my origin. So I know at the very initial time, I'm right here. And I know that in 7.4 seconds, so just before 8 seconds, I reach 82 meters, which is going to be just below 100 meters in just below 8.2 seconds. So I can estimate this here. I'll be right about here. And then another key part is to know that if I have a constant acceleration, that means I have a horizontal acceleration graph. Then a constant acceleration means that I have a linear velocity. And then a constant acceleration means that I have a parabolic position. In this case, the acceleration is positive, so I have a concave up parabola, and I can kind of estimate what that should look like. Then in my second segment, I go an additional 243 meters. This is the displacement during this interval, but this is the distance on top of the original 82. So at the end of this interval, I've gone 82 plus 243 more, and so I'm actually at about 325 meters. That is at just around 20 seconds or so, at about 19. So somewhere up here, I'm at about 325. And in this portion, I have uniform motion. I have a constant velocity. So constant velocity means that I have a linear position. So I start here at the beginning of this interval, I end here at the end of this interval, and I have a constant velocity. So that means I have a constant slope of my position graph, and I have a straight line there. Notice here, this should be smooth, and it more or less is. If you forgive my artistic abilities, we have pretty much the same slope coming in from one side and from the other side, and it should be continuous as well. Here, we're continuous, but we're not smooth. We have a jump here, which represents these jumps in acceleration. But here we have a smooth transition from parabolic into a straight line. And then in our final segment lasts the last 3 seconds or so. And we go a additional 3.7 meters. So we're going to go just a little bit farther in about that same amount of time. In this case, our acceleration is negative, so we're going to be concave down. We still need to be smooth and continuous, but we also need to be concave down. And we need to go from the initial point to the final point in that segment. And so we'll curve there. Notice here that the slope here should be 0 because we come to a rest at the very end. Just like the slope here was 0 as best as we could draw. Notice that this is a much sharper parabola representing a larger acceleration. This is a wider, slower changing parabola because we have a smaller acceleration. This is concave up because we have a positive acceleration. This is concave down because we have a negative acceleration.